Hello. So in this video, we are going to discuss clouds and precipitation. Let's go ahead and get started.
Clouds vary in shape, size, height of formation, and type of precipitation. We'll talk about those here shortly. These are the essential questions that I would like you to keep in mind. So write these down and be thinking about those as I discuss the things in this presentation. These are the things we'll have discussed in class. And so if you've already heard these in class, this will hopefully help you to remember the things that you should be able to answer if you successfully understand all of the content of this portion of Chapter 11. So what is the difference between stable and unstable air? How do low, middle, high, and vertical displacement clouds differ? How does precipitation form? These are the vocabulary terms that you should have written down in your notebooks that you should understand. If any of these stand out to you as something you're not familiar with, be sure to familiarize with those before you continue on with the presentation to make sure you're completely understanding what we're talking about. So the words are condensation nucleus, orographic lifting, cumulus clouds, stratus, cirrus, precipitation, and coalescence. So cloud formation includes, cloud formation is done, Cloud formation. As warm air mass rises, it expands and cools adiabatically. The cooling of an air mass as it rises can cause water vapor in the air mass to condense. So a strategy that I used while explaining this to my class is I asked them to think about what molecules are doing. So molecules or atoms are bouncing off of each other like ping pong balls. And as that air mass expands, you can think of having a box. And in that box, say we'll have 5 ping pong balls bouncing off of each other. As you increase the size of the box, the probability for collisions decreases. And so we think of this as temperature. The more collisions we have, the higher the temperature. The less collisions we have, the lower the temperature. We can also call this thermal energy or molecular kinetic energy. And this is essentially how, quote unquote, warm air rises. So what we're basically saying is warm air is warmer than the surrounding air. So it's more buoyant or less dense than the surrounding air. And so it floats on top of it, kind of like a boat floating on top of water. Warm air floats on top of cold air simply because it's less dense or more buoyant than the air around it. And so the colder, more dense air buoys it up, it pushes it up. And essentially that's what's happening with masses of air. As these masses of air rise, they're warmer and they include some amount of water vapor. And as the air mass cools, that water vapor condenses as the carrying capacity of that air decreases for holding water. So basically the water gets colder, or the air gets colder, can't hold as much water, so the water begins to condense. This is how condensation usually happens. We have condensation nuclei. So a condensation nucleus is a small particle in the atmosphere around which water droplets can form. So think about all the fires that are happening right now in Arizona and California. A lot of condensation nuclei are in the atmosphere. So think of little particles of smoke. It's hard to think about this because smoke is if you imagine how small a smoke particle is, it's very small. But if you think about how small a water molecule is, that's much smaller. And you can imagine, like in this picture, you can imagine water molecules sticking to the condensation nuclei, the little smoke particle. And as they start sticking to it, it's catalyzing them to come into close proximity to each other. And as they come into close proximity to each other, they're more likely to condense into liquid water. And as they condense into liquid water, they become more dense. So they can also refract light. And this scattering or refracting of light creates this visual effect that we see as clouds and also causes what we call precipitation. So a number of things caused by this. Atmospheric stability. So like I said, as air masses rise, they cool. And as they cool, the air mass will not be able to hold as much water. I forgot one other thing. Let me go back a couple slides. So when we talked about adiabatic cooling, another thing that I mentioned in class is if you think about your air conditioner or your swamp cooler, your air conditioner or swamp cooler are relying on adiabatic cooling to behave as a heat pump. And what basically happens is in your house, if you have an air conditioner, your air conditioner has a storage of coolant, Freon, or whatever your coolant is. And what's going to happen is you have liquid coolant in the house, and your air conditioner is going to allow the liquid coolant to boil or to vaporize in a closed system. And as it turns from liquid to gas, it's going to absorb thermal energy from the inside of your house, essentially. And then once it's absorbed that thermal energy, the air conditioning system will pump out that vaporized coolant to the outside of your house, to that condenser box, that big fan box that's outside of the big heatsink, that large loud box. And that large loud box is your condenser, and that condenser recondenses that gas coolant back down to a liquid. And as it does that, as it compresses it back down, it's going to release all of that thermal energy that it just absorbed. And that's why you can feel the hot air blowing out of that fan box outside, that condenser. And then once it's recondensed down to a liquid, that system pumps that liquefied Freon, liquefied coolant back into the house to complete the cycle, to repeat and to pump heat out of your house. And that's why I say your air conditioner doesn't technically cool your house. It pumps heat out of your house. Kind of like you don't dark your house. You flip light switches on to add light to your house. But darkness is just the absence of light, just like cool is the absence of heat or absence of thermal energy. All right. And a swamp cooler works very similar, but allows liquid water to turn into gaseous water. All right, let's keep going though. I'm taking way too long for that. Cloud formation. So let's just talk about this. So as air masses rise, or as air masses become warmer than the surrounding air for whatever reason, whatever this causes this instability, sometimes it's unequal heating of the Earth's surface or whatever. So the air mass will get heated somehow. And that warmer air mass, like you can see with the little thermometer gauges here in this picture, the air mass is warmer than the surrounding air. And so it's going to be more buoyant or less dense than the surrounding air. And so it's going to keep on rising until it approaches an air mass that's equal in temperature. And the same is true for the opposite. If the air mass is cold, it's going to drop, and it's going to continue dropping until the air around it is the same density or same temperature, has the same specific gravity. But for the simplicity of this, we're just going to think of it as being the same temperature. All right, so clouds can form when moist air rises. And when we're saying moist air, it just happens to be approaching 100% relative humidity. And so what I mean is air gets warmer, it could theoretically pack more water into it before it condenses. And so this idea can be fairly complicated if you want to think about it that way. But the basic idea is once the air content gets cold enough, the water content of that air will condense. So you can cause clouds to form by forcing air up, by mechanical processes, or sometimes it's caused by air masses colliding and one air mass being forced above the other. So one of these types of atmospheric lifting is called orographic lifting. And so this is something you might imagine happens in Hawaii quite often, rather constantly. We have a lot of bare open ocean, thousands of miles of ocean, and that air gets pushed along the surface of that flat ocean for a very, very long period of time. And eventually it collides with the Hawaiian Islands. And as it collides with the Hawaiian Islands, that air is forced to rise up in elevation. And as it's rising up in elevation, the air is cooling. And as the air cools, that water content of that air is going to condense along the sides of those mountains in Hawaii. And that's why Hawaii is always raining, always green. Obviously there's high thermal energy, so it's warm. And the combination of being warm and having lots of water allows a lot of really pretty plants and animals to thrive in Hawaii. And I actually watched a documentary on Disney Plus that showed Hawaii and how beautiful it is in Hawaii, and it kind of talked about this process. Let's keep going though. All right, so there's other types of lifting as well. So lifting can also happen through convergence. And if you think back to elementary school when you learned about tectonic plates, and you remember where tectonic plates can collide, and they obviously create earthquakes and mountain ranges like the Himalayas. This type of convergence also happens with atmosphere. And so imagine there's two fronts of air. There's a warm front and a cold front, we'll say. The warm front is at least slightly warmer than the cold front. And as they collide, think about which air is going to go up, the warm front or the cold front. And if you think about that for a minute, warm air rises above cold air. And so we have a massive wedge, kind of like this, kind of like in this picture here, how we have the wedge of mountain pushing the air up. but instead of the wedge in this case being mountain, it's going to be the cold front. The cold front is going to go underneath the warm front, and the warm front air is going to be forced up. And as that warm front air is forced up, it's going to increase in elevation, and as it increases in elevation, it's going to cause precipitation. And depending on the temperature difference between those two fronts, the steepness of that wedge is going to be more steep. So for example, if that cold front air is much colder than the warm front air, that warm front air will rise much more rapidly, much more violently, releasing a lot more energy more rapidly. And this is how you get some interesting things like intense thunderstorms and tornadoes, hurricanes, things like that are happening because there's massive, large surfaces of air that are colliding with other surfaces of air. And when there's a temperature gradient, you cause rapid rising, and you have a lot of that energy being released in a small amount of time, almost like an explosion of air. Let's keep going. So we have types of clouds. You may have seen an image like this before. These are different types of clouds that we have distinguished by names, and we have these different layers. Notice on the left side we talk about altitude in kilometers. It's depicted there, and the higher you go up, the colder the air is getting. And so you can imagine that the lower clouds are mostly liquid, and as you rise up higher and higher in the troposphere, you're going to run into a lot more ice crystals, a lot colder water content in the clouds. So low clouds are going to include cumulus clouds and stratus clouds, and these exist below 2,000 meters, like we talked about in this picture. 2,000, the 2 on the side, the altitude's in kilometers. So everything below that 2 is what we would consider to be low clouds, 2,000 meters down to the ground. Then we have medium clouds. The middle clouds are the alto clouds, the alto cumulus, alto stratus clouds, and they exist between 2,000 meters and 6,000 meters. And they're typically made up of a transition between ice crystals and water droplets. And then as you can imagine, the high clouds are going to include the ice crystal clouds. We're talking about cirrus clouds. We're talking about anything that exists above 6,000 meters. So cirrocumulus, the top half of cumulonimbus, cirrostratus, those would all be considered high clouds. And then we have what are called transition or vertical development clouds. So if the air of a cumulus cloud is unstable, or in other words, there's a warm front hitting a cold front, and a lot of that content of that cumulus cloud is being forced up in higher elevations, then you have rapid condensation and a lot of energy release, and that's where you end up with these clouds that I was telling you about, those thunderheads. You can imagine you have a cumulus cloud, a lot of warm air is being pushed up above the surrounding colder air, forming a massive cumulonimbus cloud. And so that usually results in rain, storms, lightning, things like that. Precipitation will usually form in this case and in other cases as well. So anytime you have water falling from clouds to the ground, that's called precipitation. That can include rain, snow, sleet, hail, and other combinations in between of those things. I mean, I've seen it rain and hail at the same time. I've seen it snow and rain at the same time. That's usually just called sleet. But you can imagine there's a lot of combinations in between. Coalescence. And this is how small particles of water kind of come together. We talked about those condensation nuclei. So you can imagine as those start getting weighed down, they might start dropping in elevation, and as they drop in elevation, they might start collecting, kind of like the snowball effect, where you take a snowball, you roll it around, and as you roll it around, it gets more and more layers, it gets bigger and bigger. Raindrops do the same thing, especially if they're being blown up, and then they're starting to fall, and then they get blown up again. They do multiple trips back up into the upper troposphere and then fall back down. You can imagine they're going to accumulate a lot of material, and these droplets can get big. Like when you're having intense storms, you may have noticed that the water droplets are huge. And that's typically because there's a lot of air being pushed upward. And as the air is being pushed upward, the water droplets are trying to fall downward. And as they're trying to fall, they're just adding more and more material because they're coalescing into bigger and bigger units. Bigger and bigger droplets, bigger and bigger hailstones, whatever it happens to be. That's called coalescence. We talked about how precipitation is pretty much anything that hits the ground. And then this all comes back to the water cycle. So in the water cycle, we talk about precipitation. Anywhere in this water cycle, evaporation can actually occur. I know it looks like evaporation only occurs when the sun's out. Off of, in this picture, it makes it look like it only comes off of lakes. Imagine anywhere in this cycle, we can actually have evaporation happening. Rain can turn into evaporation. Rain doesn't even have to hit the ground. It can actually evaporate before it hits the ground. I've seen this in Arizona. Streams, rivers, runoff, lakes, anywhere in this process, even with plants, transpiration. Transpiration is a type of evaporation. This is feeding the water cycle, and it's all powered by the sun. And so once again, these are your essential questions. In summary, you should have learned about condensation nuclei, orographic lifting, cumulus clouds,
Clouds, cirrus clouds, precipitation, coalescence. Hope you enjoyed the video. Thanks for watching. Don't forget to subscribe.